The independence of random variables. Recall when we are discussing probabilities of events, uh, two events were said to be statistically independent if the occurrence or non-occurrence of one did not affect the occurrence or non-occurrence of the other. So we take the same concept to defining the independence of two random variables and ensure that happens at all possible pairs of points. So here you have four equivalent statements of independence between x and y, and each of these is both necessary and sufficient for independence. We can extend this idea to functions of random variables. So if x and y are independent, so are g of x and h of y, g and h being any function, and like the conditional mean of x given any value of y would be the unconditional mean of x, and so on. Now, just as we did for independence among three or more events, we would do that for the mutual independence of three or more random variables. So not only would the probability of A, B, C be equal to PA, PB, PC, we would also need to establish that for all subsets. So PAB would also need to be equal to PAPB, and so on. So looking at that for the n-dimensional random variables, we have one expression for the joint CDF. So it must be the product of the individual CDFs for all possible subsets of the index set. And we could write this in terms of the joint density function, in terms of the joint characteristic function, and so on. Now, after discussing independence, let's also talk about dependence and how to measure dependence. An ideal measure of dependence between two random variables should have a set of desirable properties. I have listed a few here. Universal existence, symmetry, meaning the dependence measure between x and y should be the same as that between y and x. If I know the dependence measure between x and y, if I exponentiate both or one of them, that should not change. If my measure shows that they are fully dependent, that should imply an underlying function relationship between x and y. If the measure is 0, then it should imply independence, and vice versa. So there are several measures of dependence available. The first is covariance, which we've already seen, or covariance normalized by the product of the standard deviations, the correlation coefficient, or more completely Pearson's correlation coefficient. There are others like Spearman's rho, Kendall's tau, the sup or maximal correlation, monotone correlation, and so on. These three rhos, rho S and rho M, have a hierarchical relationship, which if x and y are jointly normal, then these three are equal. Now, the one correlation measure that is universally popular, and which is what we are going to use in this course also, is Pearson's correlation coefficient, and we are going to discuss some of its pros and cons next. But if you would like to know more, I have listed a couple of resources for further reading. Now, some of the properties of Pearson's correlation coefficient. It's bounded between -1 and +1. If it's close to 1 in absolute value, then it implies there's a high linear dependence between x and y. If it's close to 0, it means there is not much linear dependence between x and y. If x and y are independent, then the covariance is 0, which means rho is 0. Unfortunately, the converse is not necessarily true, and there are many well-known examples of that. But on a positive note, rho is not affected by a linear transformation. And it's easy to show that if I know the rho between u and v, any linear transformation x from u and y from v would give me the same correlation coefficient. Here are some of the more limitations that we discussed. Sigma 1 and sigma 2 need to be defined and need to be finite. Rho is not invariant under a monotone transformation. If there is time, we can go over one example. And as I said already, that rho correlation coefficient being 0 unfortunately does not imply independence. Although if they're independent, rho is 0, but rho equals 0 does not always imply independence.